Morning guys, this is Mr. Ndebezita once again, and this time I think we will look at the exercises. So this is exercise 1.1. It deals entirely with everything that we have done thus far in this chapter. So as you can see, there are too many problems in here. We are not going to solve every problem there is. We are just going to focus on a few. Right, so we will start with exercise 1.1. So I'm not going to solve everything in here. I think I'll solve the first one, I will solve the second one, and I will also solve the sixth one. Maybe I will go to this one as well. So they say to us in exercise 1.1, so from 1 until 6, we should find the domain and the range of each function. So we have a function in here, 1 plus x squared, and we know that this is a parabola that has been shifted 1 unit upwards. So I think we should just come here just to demonstrate what that is. So we have x squared plus 1. Okay, let's just draw this graph from the interval of -1 is to 1. Right, and then we will use this color. Let's just try to use this one, and let's just draw the graph. There it is, but it's not as pleasing as we would want. So let's increase the interval. Let's say -25 to +25, and let's see if there will be changes. Of course there it is. So I want you to see something. As we increase this has been okay. Let me just do this. Sorry, let me show you something. Let's draw first the graph of x squared. Right, and let's draw this from the interval of -25 is to +25, and we will use a different color and everything in there. So let's use a black color, and let's just draw that. So the graph of x squared plus 1 is in fact the graph of x squared shifted 1 units upwards. I just wanted you to see that. So let me just get rid of this one, undo. So what we want to do there is to find the domain and the range of this function. So we know, let me just do this. Let me just try to bring it a little bit down. We know that the domain, by just looking at this function that we have, remember the domains are the values of x, as you can see. This is from -infinity is to +infinity are the values of x. So that would be the domain in here. -infinity is to +infinity. I wanted to see whether there is a possibility of asking for that. If there is, okay, it seems like it is not possible for us to find that, or maybe there is. Okay, let me just leave that. So this is from -infinities to +infinity, and they are also looking for the range. And the range of the function, as you can see, the range are the values of y. The graph begins at 1 and it is defined at 1 going to +infinity. So you will have that enclosed bracket to show that 1 is inclusive. So we begin at 1 going to positive infinity, and infinity we will have that closing bracket because we don't know where infinity ends, so we will have that type of a bracket, but because we know where the graph begins, we will have that type of a bracket. Very, very important that we note that. In fact, I think I should just try to come where, let me just, I think I have something in here that might help us with that. So let me just look for something here. I have a software here. Okay, I don't see it, but let me look at this one. Okay guys, there it is. So let's just wait for it to load up. And what I wanted to do here was not necessarily to draw up the graph. I think we should just have let's just have this and try to demonstrate what I'm saying. So we are saying the domain is from negative infinity. Unfortunately, I don't have infinity sign on this laptop. Is to positive infinity for the domain, and for the range it's 1. So the type of bracket that I'm talking about is this one. So it will be 1 is to positive infinity. So I don't have the infinity symbol around here, so that would be the range. Let me not waste your time, that will just be the range for the first one. So I'm going to also solve the second one, 1 minus the square root of x. What I'm going to do first is to draw the graph of minus the square root of x and move that graph 1 unit upwards. So what I'm going to do is to just have a function which is minus x raised to an exponent of 0.5. I'm just going to draw that first, and I'm going to start from negative 10 to positive 10, and let's just say start and end there, and I'm going to use the very same thing. It's fine, yeah, let's use black, and let's just see that graph. So let me just come here. This is the graph of minus the square root of x. Here it is. Now from this graph, what is it that we want to do? We want to add a plus 1. A plus 1. And I want to show you the differences that we might have there. So now we want to say 1 minus, and I'm going to say x to the exponent of 0.5. Close that. So this is what we have there, 1 minus that, and here it is. So we can begin from minus 10 to positive 10, and we can show this as the beginning and that one is the end, but I'm not going to use black. I'm going to use this color, and look now what has transpired. The graph, there it begins and there it ends. Let's just try to verify that. So you see, we said, so this is the beginning and this is the end. But I want you to notice something. This one, it's the original one, and we translated this graph 1 unit upwards. So this has been moved 1 unit upwards, and there it is. So we want to find the domain and the range. So the domain are the values of x. You can see this is 0, and the graph is defined at 0 when x is 0, y is 1. So this is inclusive. 0 is 2. Look where the graph is heading, positive, infinity, that would be the domain. And the range, remember, the range are the values of y. Look at where the graph is. It's at 1, so it is defined at y in terms of the y values. So that would be 1 is to negative. Can we say negative infinity here, or should we say it's heading towards negative 1? Let's just be very careful there. Let me take you back here, and let's try to increase the interval. Minus 20, positive 20, and let's just add that. And I want you to notice something. Look where the graph is heading, and I want you to notice, let me just do this. Very good. So I want you to notice something here. There it is heading, but we can never and ever say why it's heading towards negative infinity. It has to be less than negative infinity, because let me show you something. Let me just increase, or let me decide not to specify here. So if I decide not to specify there, it will take this argument range from negative infinities to positive infinity. And when you do this now, look what is happening. It will forever and ever, we will never and ever see that. All right, so the point that I'm trying to make here is that we cannot say it is going towards negative infinity. We have to say it's less than negative infinity. And why is it so? Let's go back to the notes that we had concerning these types of functions, these ones, and let's see how the domain and the range was dealt with in this calculus book. Let me just show you those types of functions. Okay, I think I must have skipped that. Let me try to run fast. Okay, here we are. You see? So I want you to notice something here. We have that, and the domain is x should be greater or equals to 0, and x has to be less than infinity, because this is not heading towards infinity. It has to be less than infinity. Even y should be greater or equals to 0, that is true, and less than infinity. Hence I am saying to you here, let's go there very quickly. Let me just do this. So when we are here, so our domain for this function, remember our function, it's this one. Let me just get rid of this one very quickly. Let me just cut that. So when we are here, the domain would be the values of x. That would be 0, which is inclusive. 0 is to positive infinity, no doubt about that. I can see it there. and it only accommodates positive x values. So 0 inclusive is to positive infinity. But when it comes to the range, you are going to say 1 is to what now? 1 should be less than negative infinity. So we are therefore saying y in between y should be less or equals to 1, and y should be less than negative infinity. Very, very important that we understand that the range here, which are the values of y, should be less or equals to 1. There they are, those values that are less or equals to 1, and y should be less than negative infinity. That would be the range of this function. Be that as it may, I'm not going to solve this one. I'm going to do number 4. And we have this function g at x equals the square root of x squared minus 3x. Let's just try to see how that function would look like. So what I'm going to do, I'm just going to delete this. Yes. And I'm also going to delete that. And then once those two have been deleted, let's just have, remember it says this. So let me just take this. Let me just copy this, Control V and paste. But we are having a problem here. So here I'm going to do this. Very good. And one other thing, I'm going to do this. Remember, the square root is to the exponent of 0.5. And I can draw that graph. So it can begin from, let's say, from negative infinities to positive infinity. That's fine. Let's say this is the beginning and that would be the end. And let's just use a black color for that. So I'm having this function. Let me just try to bring it down there. Right. When one looks into this function from negative infinity, okay, let me do this so that we have a clearer vision. Let's say from minus 10 to positive 10. And let's draw that. There it is. The function begins there. Remember what we said. We said this should be the beginning and that should be the end. So we have a function there. It is from there. Okay, that's fine. And then from this side to that side. So what can we say here? We can say x squared minus 3x is greater or equals to 0. X squared, it's greater or equals to 3x, and then x is greater or equals to 3. And we are having that point there. Right, okay, that is fine. Now we want to find the domain. Very important. So we have this function and we want to find the domain. So you can see that the function goes towards 0. So the domain, because we have restricted the values here. Remember, so from negative infinity, don't forget that. Oh, sorry. Undo. Cancel. Let's just undo that. Very good. So we are moving from negative infinity is to 0, and it is defined at 0, so we will have that type of a bracket. The union of what? The function is defined at 3. We will have that type of a bracket. 3 is to positive infinity. That would be the domain. And in terms of the range also, we can see that it is defined at y is equals to 0 at the origin here. So we would say the range, it's 0 inclusive is to positive infinity, because we can see that immediately when we do this. It becomes very, very clear, you see. So the function is heading towards, you see what I'm referring to. It is heading towards positive infinity. So let me just have a pause I will come back just in a few seconds. So okay guys, let's continue. We have seen the domain and the range of this function. So it is very important that before you can predict the domain, because somebody might solve for x here and find x being greater or equals to 3, and you will only state the domain on this side, but you never stated the domain on that side, so it might just be incomplete. So let us continue in that, and I'm just going to solve this one. G at t equals 2 divided by t squared minus 16. But this programmable software is using x by default. Let me show you why I am saying that. So let me just delete this, and let me just come here and show you something. When I say y equals let's say maybe 2p, and we try to graph this, let me show you what it will do. You see, it doesn't recognize the constant p, but if you come here and you say x, it will recognize and it will be able to draw the graph. So it is by default using the alphabet x, but that is fine. I was just trying to show you that. So let's go here and try to find this. 2 divided by t squared minus 16. So I'm going to use x for that. So I have the following. So let me just come here and just say a function. So I'm going to say 2 divided by x squared, x squared minus 16 minus 16. It is very important, or to be very sure, let's see whether it will do what we want. Okay, there it is. So let me just do this just to ensure that I don't run into any problems. Let me just do this and see whether we will still get the same result. There it is. Okay, we have this function, as you can see in here, and this is the function of g at t equals t divided by t squared minus 16. And somebody might just come here, t squared minus 16 is equals to 0, t squared equals to 16, and t equals plus or minus 4. And there it is, you will have plus or minus 4, so minus 4 and 4, and you would just say your domain is that. Somebody might want to look at that, but I prefer the graphical way of representation because it becomes very easy to notice the domain and the range. So you can see that where the graph is heading from negative infinity in terms of the domain is to positive infinity. But there's something that I think we should look at here. Because we are speaking in terms of the domain. How many pieces do we have? We have 3 pieces. Here they are. So negative infinity is 2, is minus 4 included, of course, minus 4. So negative infinity is to positive infinity because even 4 is defined there. So this would just be the domain. Negative infinity is to positive infinity, and the range would also be from negative infinity is to positive infinity, because we have a value of y at x is equals to 0. So it is defined at x is equals to 0 there. Okay, that's fine. The rest is for you great people to solve. Where we have made mistakes, you are more than welcome to correct us so that we may share knowledge and understanding. Very important. Now in exercise 7 and 8, which of the graphs are graphs of a function of x? So as a function of x, so that is just simply to say, for example, y equals 2x. So f at x, which is y, is a function of x because y is equals to something x. So let's look in here. In in exercise 7 and 8, which of the graphs are graphs of the functions of x? So we have this function, we have x and we have y. So y is a function of x. So this is in essence a function of x. So it doesn't ask us whether these are functions or not. So this would be categorized as a function of x because y functions with the variable x. So the values of y are dependent upon the values of x. And we have the x and the y, so y is a function of x. And then from there we go to number 8, and this is also a function of x. Which ones? And give a reason for your answer. So it seems like, based on the Cartesian plane, of course, I'm reasoning based on the Cartesian plane. For every value of x, you would get a corresponding value of y. So this is a function. Sorry. Y is a function of x, but this is not a function because it touches more than once. For one value of x, you have more than one value of y, so this is not a function. So maybe they are saying which of the graphs are graphs of the functions of x. Now remember, for this to be a function, it has have to have a one-to-one relationship. For one value of x, you ought to have only one value of y. So in that context, this is not a function. Why? Because for one value of x, you have more than one value of y. So in that context, it is not a function. And this one is a function because it passes the vertical line test. This one fails the vertical line test because it intersects the value of y more than once at the same value of x. So this one, it passes the vertical line test, therefore it is a function. This one is not a function for the same reasons we have provided on behalf of this one, and this is also not a function. It fails the vertical line test. For one value of x, you have more than one value of y. If we look at it in that context, I will assume that's what the question requires. Okay, and then we come here. I'm going to solve this one and that one, leave number 10 for you. Express the area and perimeter of an equilateral triangle as a function of the triangle's side length x. I know an equilateral triangle, it's a triangle with all three sides equal. So when they say express the area and the perimeter of an equilateral triangle as a function of x. Now remember how an equilateral triangle looks like. Let me just try to see whether I can have a software that can allow us to have that shape. I have some softwares in here, but I'm looking for a mathematics one. So let me see. I do not think that I have it in here, but we know, unfortunately, I don't have time to do that. We know that the area of a triangle is equals to half base multiplied by perpendicular height. So what I'm going to do, let me go to a weight pad. Let me just quickly go to this one, and this is what I'm going to do. So I know that area. Okay, let me use a capitalized letter. Area equals half, which is 0.5 base multiplied by a perpendicular height. Let me just say height. I know this is the formula for area, but I know that the perpendicular height, I will have to cut this side into a half. So remember the side length is x, so I will have 1/2 x. So I think let's not do it now, because now I'm going to confuse you. I think I'll do it on paper, and then when we carry on the second tutorial, we will just discuss all this. For now, let's just leave them. Let's just concentrate on those which we can solve. Right. Even this one we will not be able to do so, because they say a point P in the first quadrant lies on the graph of the function this. Express the coordinates of P as functions of the slope of the lines joining P with the origin. So we will do that. We will do that in the next tutorial. So I'm not going to deal with these ones that requires writing L as a function of y. We will do them on the second tutorial, because I don't have those computer pen where I can write on the screen and demonstrate. So I have a lackage of tools. I lack in terms of the tool. So let's just leave them as they are, and then we will continue, of course, and we will come to functions and graphs. Find the natural domains and graph the functions 15 to 20. So the natural domains, which means the values of x which are natural numbers, so starting from 1 going there. So find the natural domains of the graphs. Find the natural domains and graph the functions, these ones. So we can graph that one and find the natural domains. So when they say natural domains, it simply means we cannot accommodate negative numbers, and we cannot also accommodate 0. It's not a natural number. So in our interval of domains, we have to move from 1 to positive infinity, because that's how the natural numbers works. So what I will just simply do is to just delete this and just have that function, which is 5 minus 2x. So I'll just say 5 minus 2x and just see how that graph would look like. So I will not specify again. So meaning I'm drawing this from negative infinity is to positive infinity first, so that we may see what is happening here. So let me just try to explain. So we have a straight line, y equals mx plus c, the gradient is minus 2, and the graph intersects at y is equals to 5, and there it is, our y-intercept. So you can try to move this as many times as you have, but they say here find the natural domains. So let's see what the natural domains would be. Remember, the domains are the values of x. So we have the intercept there, but please let's not forget that we have values there. So I know natural domains deals with natural numbers which begins with 1. So please be very careful there. So I would say, okay, the domains would be from 1. Natural domain would be, but let's not say that. Let's not say that, because since we have it in there, let's just say it seems like this is 2.5. I don't know exactly the x-intercept there, but we can try and find it. X-intercept y equals to 0, so you will have minus 5 equals minus 2x, and then you would divide by 2. Yes, it's 2.5. So we would have this 2.5 there. So the graph, but remember it's natural. Find the natural domains. And 2.5, it's not a natural number, it's a rational number. So it's not a natural number. So if we have to look at the natural domains, you see we can move from 1. We can move from 1. We have a point there. So natural numbers begins with 1. So we can say domain is 1 is to positive infinity for the domains here. Is it only the domain that they wanted? Yes, the natural domain. Okay, that is fine. Let's look at this quadratic parabola that we have there, where the coefficient of x squared is negative. So this is 1 minus 2x minus x squared. So let me just do this. So we have 1 minus 2x minus x squared. Let me see. 1 minus 2x minus x squared. And I'm going to use this for drawing. And I'm going to use that color. And I'm not going to specify here, but I want this to be the beginning and that one to be the end. And let me just move a little bit on this side. So let's check something there. So the y-intercept is 1. Do we have that? Of course. So the graph will turn at 2 is to minus 1. These are the stationary points, but we will deal with that some other time. So here we are, we have a function and we want to find the natural domains. Now remember, the natural domains deals with the natural numbers. So what we will do, since the natural numbers begins with 1, let me just come here. So I will say 1 is to positive infinity. Remember, because if I keep on doing this, you see, I want you to notice that it keeps on going to the right. You see, keeps on going to the right, keeps on going to the right. So we will just say the natural domains of this function will be from 1 to positive infinity. Right, okay, that is fine. I'm going to look at this one. Unfortunately, this one we will have to do it some other time, because this graphing program that I have here cannot interpret what the modulus sign is. So I will not be able to solve this for now. We will have to go to this one, the square root of minus x. So what I'm going to do is to just come here and just say the square root of minus x. So what I'm going to do, I know the square root of minus x, so I'm going to say minus x to the exponent of 0.5. That would be the square root of minus x. So you have minus x, there it is, raised to the exponent of that. And let's see the type of a graph that we have. And remember that I've drawn this from negative infinities to positive infinity. So you can see that the function is defined at x equals to 0. So 0 inclusive is to, can we say negative infinity? No, remember we are looking at natural domains. So the natural domains, because the natural numbers cannot be negative here, we can just say the natural domains does not exist since x is negative on this side. So we do not have any natural domains. Okay, that is fine, and we cannot be able to solve these ones for now. Let's go to this one. Find the domain of y equals this, x plus 3, 4 minus that. So let's try to do that. So I'm going to take this one as the numerator. So let me just delete this and let me just edit this one. So let me just do this. I have this x plus 3 inside of the brackets, and this has to be divided by what? The square root 4 minus the square root of x squared minus 9. So 4 minus I'm going to say 4x minus 9 raised to the exponent of 0.5. Let me check whether this is correct. X squared minus 9. Sorry, this is not 4, this is x squared. So let me just do this, x squared minus 9. There it is. And just to be safe, let me do this just for safety purposes. And this is the function that I have. And be very careful that I've drawn this from negative infinity is to positive infinity. So I am looking for the domain, right? And these are not the natural domains, by the way. So it is defined at -3. So -3. So we are moving from negative infinity is to -3. The union of 3 and a quarter, sorry, 3 and a half is to negative infinity. That would be the domain. So negative infinity is to -3, the union of 3 and a half to positive infinity. And then once that is done, please do try to practice this one. And then graph the following equation and explain why they are not functions. Unfortunately, we will not be able to do this one. And this one, we can graph this one. Y squared equals x squared. I can introduce on the square root on both sides. And when you do that, the square root and the 2 will cancel out. And then you will have y is equals to x. And I can draw that function of y is equals to x. I can draw that function and I can have it as a straight line there with a positive gradient, and I can therefore state, graph the following and explain why they are not graphs of the functions of x. Okay, let's wait a bit here. Graph the following equations and explain why they are not graphs of the functions of x. So y squared equals x squared. Okay. So when I introduce the square root of both on both sides, it gives me that. But they say graph the following equations and explain why they are not graphs of functions of x. So we have an equation here, y squared equals x squared. Okay. So for every value of x that you square, you also get the value of y that is squared. So for example, let's take -2 squared. So -2 squared will give me 4, and 4 squared will give me 16. And for example, if I take -5 squared, it's 25, and 25 squared, it's a very big number. So they say graph the following equations and explain why they are not graphs of the functions of x. And unfortunately, in our function machine here, let me check whether we can. No, unfortunately we cannot do it in here. We will have to solve this problem. Sorry, let me just close that. So I think we will also solve this one on the next tutorial. Let's just leave it as it is for now. Even these ones, let's just leave them, and then we can go to piecewise defined functions. So graph the functions in exercises 25 to 28, and they want to have that. Now we are going to graph them. Nothing is mysterious about this. f at x equals x for x is less or equals to 0, sorry, x is greater or equals to 0, and x is less or equals to 1. So x is in effect between 0 and 1 for the first one. So let's try to specify this on this graphical representation. So let me just get rid of this and also modify this one. So I have a function here, y is equals to x. There it is a straight line, but the argument range, they say x should be greater or equals to 0. Okay, so 0 is included, and then where should it end? X should be less or equals to 1. There it is. And let's just try to draw that graph. There it is. So this is just the beginning and the end. Let me just do it in this way so that you are not confused. Don't save. So let me just do it in this way to show just that this is where it ends and where it begins and where it ends. So I have it like this. There it is. Because they said graph these functions for this one. And 2 minus x is also a straight line. So I can come here and I can have 2 minus x. Now let's look at the interval. X should be greater than 1. So let's go to 2. And then I will use whole number integer values there. And then x should be less or equals to 2. Sorry, where am I? X should be greater than 1. Okay, sorry, less or equals to 2. There it is. And I'm going to use a different color, which is black, and this. And let's look into that. Where is it now? Undo, redo. Where is that function, guys? We have 2 minus x, and x should be greater than 1, which is at 2. There it should begin. And then they say to us x should be less or equals to 2, and there it is. So let me say start, and let me also say end. There it is. There it is. So we have this function 1 is to 2. It becomes very clear now. So we have been able to graph that. Nothing is new with that. So I'm not going to solve this one. And this one, I will leave it for you. I'm going to do this one. So g at x equals 1 over x. So I can just come here, just edit this one. 1 divided by x, and let's look at the interval. X should be less than 0, so let's say from -1, and okay, that is fine. Let's just draw that. X should be that. Let me just draw it and see. Now we are having a problem because it also includes the positive side there. Why? Because of this. So here we are saying x should be less than 0, so meaning x should be negative. There it is. But now we need to specify on this side where it should end. Where it should end. Because we want to get rid of this side. We honestly want to get rid of that side. Because we have 2 minus x. Let me just get rid of this. So we have this piece, but now it is even moving to positive infinity. And I want to not include that. If I say 0 here, yes, it is excluded. So that is fine. We are having the function 1 over x, which is a hyperbola, and the value of a is positive. It will be on the first quadrant and on the third quadrant, but no, because we are just looking for that portion only where x is negative. All right, that is fine. And then we have another function which is x, and in this function x, where x is greater or equals to 0, so it should start from 0 towards positive infinity, because all those values going to the right are greater or equals to 0. So we can draw this. There we have it. Very important. So we have drawn g at x for 1 over x if x is less than 0. This is the portion. Remember what I said here. I just said this is where it should start and where it should end. And remember, it cannot end because it is heading towards negative infinity. And I can also specify the same for this one. I can say start here and end there. And I can use a different color there. Maybe I can use black. And there we have it. And this one also moved towards positive infinity. So these are the piecewise defined function for that. So that it's fine. We're not going to stress ourselves a lot. And then we come this side. Let me just show you something. We will deal with these ones at a later stage. And then we come to these ones, increasing and decreasing functions. Graph the functions in exercise 37 to 46. What symmetries, if any, do the graph have? Specify the intervals over which the function is increasing and the interval where it is decreasing. And we will start with the very first one. So let me just do this. Let me just get rid of this. Yes. So the first one is y is equals to minus x3. So I'll just come here and just say minus x to the exponent of 3. And I want to do this. And I want to draw that. And this is the function that I have from positive infinity to negative infinity in terms of the values of y. And what is it that I want to do here? Now the question says graph that, which is what I have done, and it was never specified the interval there, but I just want us to specify it for ourselves here. Let's say we start from minus 10 to positive 10, and let's draw that, and so that we can have something okay, that's fine. We have this, right? And then what is it that we want to find out here? What symmetries, if any, do the graph have? Let's look if there are any symmetries. We know that this function is symmetric about the origin. Very, very important that we understand that. And the coordinates in here matches the coordinates in there. And one thing that we need to note, because it's an odd function, and the odd function are symmetric about the origin. We learned that. Right. Secondly, we have specified the symmetry. Okay, specify the intervals over which the function is increasing and decreasing. So let us look at the function. Remember, the function increases if f at x2 is greater than f at x1, therefore the graph is increasing. And if f at x2 is less than f at x1, the function is decreasing. So let's just pick any values in here. So I'm going to call out a calculator so that it may help us to understand this. So let's just pick any values in here. I can see that the function there, it is increasing, and there it is decreasing, but I'm looking for the interval. So let me take f at minus 2. Do I have a function? Yes, I have a function. So I know the function is minus x to the exponent of 3. So let me take minus 2 and raise this to the exponent of 3. I get 8. This is the value that I have. So suppose this is my x2. Let me have my x1, which is minus 1, and see what value I will have. Minus 1. And I get 1. So because f at x2 is bigger than f at x1, the function is increasing. On what interval? The function is increasing from 0, very important, from 0 in terms of the x values, because f at x2 is bigger than f at x1, therefore the function is increasing. On which interval? On that interval of minus 1 and minus 2, because I have substituted the integer values of the domain, which is minus 1 and minus 2. So the graph is increasing like that, and let's just try to see something. You see it keeps on going to negative infinity. So the graph is increasing from 0 is to positive infinity. Sorry, negative infinity. The function is increasing. Very, very important. But in terms of just those minimum intervals that I have used, I can say the function is increasing on the interval minus 1 is to minus 2. Very important, we saw that, because f at minus 2 is bigger than f at minus 1. Therefore, the function is increasing. Let's check if the function is decreasing. Suppose we take the values 1 and 2. And this becomes my x1 and this becomes my x2. Let's check what we will have. So let me come here and now use a 1 there. And I will get negative 1. Now let me go and use a 2 now. And I get minus 8. So f at x1 is bigger than f at x2, because I know that minus 1 is bigger than minus 8. So because f at x1 is bigger than f at x2, therefore the function is decreasing. Or because f at x2 is less than f at x1, therefore the function is decreasing. Aye, Professor Makeba, this is very good. Now we understand the concept of increasing and decreasing in that way. That's how it was explained by Professor Thomas. Let's continue. I don't know Thomas, guys. I'm very sorry. I don't know the guy. Right, we can go to 38. I'm going to do it. I'm not going to do 39. That's for you. We don't have a good graphing calculator to do this one for us, we could have done it. And I will do these ones, and I'll try to do maybe this one. I'll just see how we work into this, but I can see that we have a minimum of time, so I'm going to cut this video here, and then when we go to the second tutorial I will continue in this. So please let me see you in the next tutorial. Okay guys, let's continue. I remember we ended up in this one, so let's try to investigate this one. So this is just y. Let me just try to put this on the side. So let me just try to draw that one, and remember it's y equals minus 1 over x squared. So this is minus 1 divided by x squared. So how do I show that? Divided by x squared. So I can just do this x to the exponent of 2. So I have 1 divided by that. But let me do this just to be very safe. Now I am safe in this way, and I can use maybe this color, and I can use that. Let's just show this as for the beginning and the end. Minus 10 is to positive 10, and let us try to look at that. So here is the function that we are having, and as you can see that this is the function y equals minus 1 over x squared. There it is. Now the question said what symmetry, are there any symmetries, if any? So let us check. So here we are, and we have this function, right? What is it that we learned in the parabola? We learned, or we were told, that the function y is equals to x squared is symmetric about the y-axis, and we were shown that. But even here we notice something very similar. I know symmetry along the y-axis, only the value of y changes the sign. So let's try to investigate that. So I'm just going to bring in a notepad so that we may investigate that. So let me just go in here, and let's look at something. Let's take in the values here. Let's say for x equals to 1. Okay, I want to show you something. I want you to notice what is happening here. I want you to look here. So I want to stand exactly at x equals 1. So do you see? When x is equals to 1, y is equals to 0.07. But I want to stand somewhere here. So let me go a little bit. Yes. When x is 1, y it's negative 0.71. Very important that we understand that. 1 negative 0.71. So we have 1 negative 0.71 as the point there, right? So let me repeat that. There it is. When x is 1, negative 0.71, we have that point there, right? And I know that point corresponds with a point on this side. I know that when x is 1, let's check very quickly. When x is 1, I can have that point of, when x is -1, I can have that point of -0.71. Please try to see what the point that I'm trying to make here. For a point here, you will have a point there. But remember, symmetry along the y-axis, only the value of x changes the sign. So the value of y will remain the same, but the value of x will change the sign here. It was positive this side, it will be negative on that side. So this is also symmetry along the x-axis. Very important that we try to see that symmetry along the y-axis. And then again, specify the intervals over which the function is increasing and where it is decreasing. Now let us look at that. I know that the function is increasing if f at x2 is bigger than f at x1, and it is decreasing if f at x1 is bigger than f at x2. So I can see that the function is decreasing, as you can see, but let us try to investigate that. So I will come here. I know that I've been provided with a function -1 over x squared. So I'm going to say -1 over x squared, and I'm going to choose some values. So let me just pick a value. For example, let me say for -1, x equals -1. So I'll have -1, that is squared, and I get -1. So when x is -1, y is -1. This is my f at -1, which is -1. So let me take the second one as -2 and check what value I will have. And I get a value of negative 0.25. So which one is bigger? Negative 0.25, it's somewhere there. When x is -2, y is somewhere there. So check what is happening. We said this is the first value, x1. There it is, it's -1. When x is -1, y is -1. We have a point there. And when I say -2 now, I get a value that is bigger than -1. So because the value of f at x2 is bigger than the value of f at x1, therefore the function is increasing on that interval. It is very important that we can see that the function is increasing. On this side, the function is increasing. On that side also, the function is increasing, and we can check that. Let's take x for 1. For 1, we get -1, and let's take that for 2. Sorry, let me do this. For 1, we got -1, and for 2, we get that. So f at x2 is bigger than f at x1, therefore the function is increasing on that interval. Very important that we notice that. So we can just use the interval, for example, -2, -1, 1, and 2. It will show that the function is increasing on that interval. So that is very much fine. Sorry for opening that. Okay, we can continue in this, and where can we go now? I'm not going to do that, that will be left for you. Let me just do these ones. Minus 4 the square root of x. So we can look at that. Minus 4 the square root of x. So let me just come here and just have minus 4 x to the exponent of 0.5. I can have that, and let me just get rid of this. Right, so here we are. I am having this function, and remember I've drawn this. Let me just see the interval there. It's from minus 10 to 10. So one thing that I want to find out from that is whether there are any symmetries. First of all, I need to check what I'm dealing with. And this, remember, this is not even nor odd. This is not even nor is it odd. Let's try to look at this one. What symmetries? Okay, remember, sorry, we are just dealing with increasing and decreasing. Sorry for that. So let's check for any symmetries. Is it symmetric to anything? No, I don't see any symmetries in this. There's no symmetry for that. Or can we say it is symmetric about the x-axis if we were to draw another piece on the side? Therefore it will be symmetric about the x-axis. That's another possibility, but for now, because we do not have two pieces, we will just say there are no symmetries on this one, because even the examples that we were provided with, it was a parabola. Therefore we were able to see the symmetry along the y-axis. So this one, this function, we will just say it has no symmetries. There is no symmetry. And then specify the interval over which the function is increasing or it is decreasing. We will investigate that. So we have used the interval for ourselves. Remember to say from minus 10 to 10. So let's just come here. I know I have an equation which says minus 4 the square root of x. So we have minus 4 the square root of x. So let me take the value of x, for example. Remember I said from minus 10 to 10. So let me take a value. I will say I want you to notice something here. Oh guys, I'm trying to pull this thing down. Right, so even if you can specify from minus 10 to 10, it never and ever goes to the negative values of x. So this is just a waste of time. We can just do this and nothing changes, as you can see. So the function begins from 0 going to that side. So let's try to see whether it is increasing or whether it is decreasing. So what I'm going to do, I'm going to take the value of x as 1 first. So I'm going to substitute 1 there, and I find negative 4. And then I'm going to substitute x2, which is 2, and I find, remember in the previous one, delete 1, I find negative 4, and for this one I find negative 5. And what does that tells you? F at x1 is bigger than f at x2, therefore the function is decreasing. This is very, very important. We substituted the first value, which was 1, and we found minus 4. And I know that this value is bigger than minus 5. So I go to 2 and I find minus 5. So f at x1 is bigger than f at x2, therefore the function is decreasing. So it is a decreasing function. I just hope that we understand that. So the function is decreasing there. Okay, and I'm not going to do those ones, that is for you. And then we come to even and odd functions. In exercise 47 to 58, say whether the function is even, odd, or neither. Right. So let's see this function f at x is equals to 3. F at x is equals to 3. And I can choose any interval that I want. And let's see what type of a graph I will have. And now the question says, say whether the function is even or odd. And I have this y is equals to 3. And you have this where the gradient is 0, many would say. So for every value of x, you get exactly the same value of y. So is this even or odd? The rule goes on to say if it is even, f at minus x should give you a positive y value. If you substitute a negative x value, you must get a positive y value. And if it is odd, if you substitute a negative x value, you should get a negative y value. So there is no formula that is provided for us here. So this is neither even nor odd. Alright, let's look at 48x to the exponent of minus 5. X to the exponent of minus 5. And let's see what we can get. There it is. Is this even or odd? Right, remember this is minus 5. Alright. So we know even numbers, we also know odd numbers. So there is no odd number that is negative. Remember, we start from 1, 1, 3, 5, 7, and so on, even 2, 4, 6, 8, 10. So this is neither. Why? Because the exponent is negative there. This one, it's even. Why? Because if I substitute a negative x value there, I will always get a positive y value. So this is even. It's an even function. Alright. This is also, let me not conclude very fast. Let's check that one. X squared plus x. So suppose I substitute in minus 1 also there. I get a positive. Let me increase the values. Let me use minus 10 and also there minus 10. So it is even. This is also even. So I'm not going to do those ones. You'll do them. I will do this one just to check whether it's even or odd. Give a reason. I'm already giving reasons by showing the calculations there. So let us try to look at that one. Let us just try to look at this one. So you have x, let's substitute minus 10, and we divide that by minus 10. That is a squared minus 1. So this function is odd, and so on and so on. Okay, that's fine. We will deal with this on the next tutorial, because I have to write this on a paper just to show you what is happening. So guys, I think we are done with the first chapter, which was 1.1, and I will see you in 1.2.